Thanks, Claudio. So this is a joint work with Roy Livni and Ishai Mansour. Since it's the last talk of the session, let me just start off with the setting, which is very simple. So it's a multi-arm bandit problem. There is a learner and an adversary. The adversary picks an arbitrary sequence of cost functions, C1 up to C capital T. Notice that this is the non-stochastic version of the problem. The functions are not stochastic, they are not sampled. These are arbitrary functions. And they are defined over a set of actions X, and maps them to the losses in 0, 1. For the purpose of this talk, think about the set X as a subset of the 0, 1 interval. And the learner then interacts with these functions sequentially at rounds 1 up to t. So it picks an action xt from this set and observes the loss, ct of xt, and then incurs, and he observes only this number, so it's a bandit problem, and he suffers this loss. But in the multi-arm bandit with movement cost problem, he also, the learner also suffers an additional loss, which is equal to the distance between his current action and his action from the previous round, and the distance is measured by metric delta. For the purpose of this talk, think about the delta as just the natural metric over the interval, which is just the absolute value of the difference. Okay, and then the regret is defined as usual. But now there is an additional term that sums up the movement cost incurred by the learner. And notice that the benchmark does not suffer any movement cost because we compare ourselves to fixed action, which does not move at all. Okay. So this setting generalizes, obviously, the typical multi-arm bandit problem, which has no movement costs. And in this case, we know that the optimal regret scales like root kt. It also includes, in a special case, the multi-arm bandit problem with switching cost, where there is a fixed unit switching cost for moving between any two pair of actions. Then we know that the regret scales like k to the 1/3, t to the 2/3. I will also mention that there are a couple of related work by Kleinberg et al. And Bubek et al. About Lipschitz multi-arm bandits over metric spaces. There, the loss function is Lipschitz, and there are no movement costs, hence the setting is quite different. In our case, the metric is used to define the movement cost. And the full version, it's worth mentioning, the full version of the problem, full information version of the problem, which is completely well understood for any metric and can be solved, for example, by the follow the lazy leader algorithm of Koren and Pala. Okay, but back to the metric of interest. We can obviously get a lower bound from here by lower bounding the metric and upper bounding it by this metric and get an upper bound. But I claim that there can be a significant gap between the two bounds. And before I elaborate on that, let me just describe a motivation for this work, for this kind of metric. When can it arise? So think about an adaptive pricing problem where the learner is now a seller with an unlimited supply of a single item. And the adversary chooses a sequence of T buyers arriving at rounds 1 up to T. And in this setting, the xt is now the announced price by the seller at round T. And ct, the loss function ct, is the negative utility of buyer T. So ignore the fact that these are reward functions rather than losses. The loss function looks like this. So it's linear up to the point, up to the value, the private value of the buyer, which is the maximal price he is willing to pay. And from that point, it's 0. So this is the kind of loss functions used in this application. And the feedback is a bandit, roughly speaking, bandit feedback, because we don't get to see, the seller never gets to see the private value. It just gets to see whether there was a purchase or not. Okay, and this problem can be reduced to a multi-arm bandit via simple discretization, and this has been done by Kleinberg and Leighton. And it turns out that a choice of discretization size of t to the 1/3 actions leads to an optimal regret of t to the 2/3, and this is tight as shown by Kleinberg and Leighton. Here there are no movement costs yet, Now, to see where movement cost arise, consider the case where the buyers are patient. They are allowed to wait for, say, 2 rounds before deciding whether to buy or not, and then they can pick the lowest price. Okay? So they can stay in the store and decide when to purchase and whether to purchase across 2 time slots. Okay, so now it's pretty intuitive that sudden changes in the price can cost the seller a lot, because a patient buyer, a strategic patient buyer that waits for these 2 rounds, can simply pick the lowest price and save this difference, which is the movement from xt minus 1 to xt. This argument can be formalized, but that's the intuition. So this setting was introduced by Feldman et al., and they gave a t to the 2/3 lower bound even when there are just 2 prices to pick from, no full discretization. And naively, we can get an upper bound of t to the 3/4 by reducing it to a multi-arm bandit with switching cost problem. And there is a significant gap between the 2 bounds. And the question we would like to answer is whether we can get tight bounds for this adaptive pricing problem, and more generally, tight bounds for a multi-arm bandit with movement costs over the entire interval 0, 1. Okay, so here are the results. We introduce a new algorithm we call the slowly moving bandit algorithm. For k actions in the 0, 1 interval and the interval and the natural interval metric, we get this regret bound. So we get this additional term of t over k. And when we apply this to the entire 0, 1 interval via discretization, we get this tight regret bound, the same discretization as before, which is tight even without movement cost. So introducing movement cost to the problems did not change the complexity of the problem at all, which is kind of surprising. And finally, we do a formal reduction, as I sketched before. We reduce the pricing problems to the multi-arm bandit with movement cost problem, and we get a tight t to the 2/3 regret, which again is tight even without patience for the buyers. It's tight, so the patience of the buyers doesn't affect the worst case complexity of the problem at all. Again, this is pretty much surprising. Okay, I have 1 minute, so let me just give you a glimpse of the idea behind the algorithm. So the high-level idea is simply to make large movements with low probability. So we will make a movement larger than some d with probability proportional to 1 over d for any d. Okay, and how can we do that? So first, as a first step, we will upper bound the metric delta with a tree metric, where the tree is complete binary tree. We will take the k actions as leaves and build a full binary tree on top of them, where the left top subtree corresponds to the left side, the left half of the interval. The right one corresponds to the right side of the interval, and so forth. So the tree has low k levels. Now the idea now is to employ some lazy sampling technique that keeps the ancestor from the previous round with very high probability. So we will keep the ancestor of our previous actions from last round on the top level. We will switch it with low probability of 1 over k. We will switch these ancestor in the next level with probability 2 over k, and so on and so forth. And we will accept changes in the bottommost layer with high probability, let's say 1/2. So we will allow frequent updates in the bottom layer, but infrequent changes in the top layer. And a simple argument shows that the expected movement cost is roughly 1 over k up to a log factor. I will stop here. Yeah. And I will just mention that in a recent follow-up paper, we extend these bounds for any metric over a finite metric space, and the complexity measure looks now like this. This is the complexity measure of the metric. It has to do with the covering and the packing numbers of the metric. I will be happy to elaborate on this offline. That's all I have to say for now. Thank you.
Quick question?
the tree won't necessarily be binary and complete. So I mean, it's for the first result, it has to be binary and complete. It sounds like a technical condition. I mean, it becomes more involved when the trees can be very weird. But basically, this result also reduces back to a tree metric and follows the same lead, but the analysis is very, very different.
Another quick one?
Yeah, Manfred.
Did you really use the tree, or just the fact that the layers, the distance was twice as big?
Yeah, so it's actually a
You did use the tree, right?
What do you mean, did you use the tree?
You use the tree that, if there was left branches as you're going up versus a right branch.
No. Yeah, just the fact that it's called an HST tree, that the distance kind of grows exponentially. Yeah, that was the main property.
Okay, let's thank Tomer and all the speakers of this session.